In this lecture, I'm going to talk a little bit about exceptions, which are part of the Symphony of APIs chapter of the book. Specifically, I'd like to talk in general about why exceptions occurred, and then how do we deal with them. And for those 2 points, the coverage would be general. What are exceptions? What are the strategies? Defensive one, exceptions one, not necessarily related to any particular language. And then the 3 other points, we'll talk about handling them in Java, and I'll do that through an example. Interestingly, in Java, the handling of exceptions is done in an object-oriented manner. So every exception has an object associated with it, and when an exception occurs, an object gets instantiated, and we can benefit from the inheritance hierarchies in Java to catch generic exceptions or particular exceptions. So let's start. First of all, what are exceptions and why do they happen? So the story starts with a troublemaker, if you like, that triggers an incorrect operation. It could be the programmer. The programmer could be telling the CPU to divide an integer by 0, could be telling it to read a file from an SD card that the end user removed it from the phone. It could be the environment. An app could be connecting to a website, but the end user have turned off cellular data, something like that. So typically one of those 3 would trigger what I'm calling an incorrect operation, an operation that is not intended, all right? That's not part of the algorithm. And this operation will transfer to the CPU, and now that we're here, we're asking the CPU to execute this incorrect operation. Sometimes, in the eyes of the CPU, there is nothing wrong with the operation. For example, you may want incorrectly to take the square root of a negative number, right? The CPU has no problem with that. It says, yes, I know the answer. The answer is not a number, and it continues like that. So if the incorrect operation triggered by the program does not bother the CPU, execution will continue because the operation is valid in the eyes of the CPU, and in that case, we end up with a latent logic error. That means the program will run without problems, yet the output is incorrect. And those, as you know, are the worst kind of errors because they have no visible feature. You just get the wrong answer, and unless you have an oracle to compare with, you don't know that you got the wrong answer. On the other hand, if the incorrect operation requested by the program is invalid in the eyes of the CPU, such as dividing an integer by 0, such as reading from a file that doesn't exist, all right? Then the CPU says, that's it, I'm not doing this, and we say it throws an exception. That means it deviates from the normal flow of the data path and requests the operating system to kick the program out of memory. So that's what happens when an exception is thrown. In this case, if your program is not handling exceptions, or as they say, it doesn't catch the exception, then the operating system will indeed kick the program out of memory, take over, produce a very generic message, something like sorry or app stopped working or something. We call that a runtime error. So unlike logic errors that are hidden, invisible. They have no visible manifestation. A runtime error has a clear manifestation. We call it a crash. The program crashes and it stops working. And for the end user, this is really a terrible thing to happen. Why? Because if I'm an end user and I got a runtime error, typically this happened with a very generic message, as I said. So it's not like we're telling the user, oh, you forgot to put the SD card. No, it will say something very generic, and in the case of Android, it will say, sorry, your program, your app stopped working. So the end user has no mean of recovering from something like this. Runtime errors are also embarrassing in the eyes of the developer because it means their code is not working. So we always like to be able to catch whatever exception is thrown by the CPU. And once we catch it, we go to a part of our code known as the exception handler. And that part will either find other ways of continuing the program. For example, the algorithm may allow things to happen in one way if a file is present, and in a different way if a file is not present. Then in that case, the handler will direct the code to go in the other direction. Or at least, if nothing can be done, then the handler will be able to talk to the end user and tell him in a clear language what happened. It could say something like, please insert the SD card, please turn on the cellular network, something like that. So we always like to end up with a handler. All right. So this is the story about exceptions. Why do they happen? How do they happen? And what should program do to prevent them from leading to a crash? And whatever I said applies to any programming environment and any language. Back to the strategies for handling exceptions. We recognize two types. One type is known as the defensive strategy, and one type is known as the exception-based strategy. And let me give a general example, not related to programming, because in real life, you handle problems generally in one of those two ways, either defensively or on an exception basis. So what's the generic example I'm thinking of? Many transit systems these days allow the user, rather than paying for the trip, to tap a card, all right? Presto card, for example, in Toronto Transit. And once you tap it, that means you have effectively paid for the ride. Now, you can enter the transit vehicle from the back door or from the front door. There is no guarantee that you are really going to tap it, right? To tap this card. So how do we prevent people from just getting a free ride on the system because they don't tap their cards? Well, there are two ways. One way is to have a person standing next to the front door and another one standing next to the middle door, or if this is a train, next to every door, making sure that there is no way to get on the bus or on the train except by tapping, right? You can have some barrier that will open, if you like, automatically only if you tap, something like that. In this scenario, which we refer to as a defensive strategy, you are sort of assuming that every person is a potential troublemaker who's trying to get a free ride. And so you're telling that person, I don't trust you, so I'm going to enforce a mechanism to ensure that you're going to tap the card. This is a defensive strategy. An exception-based strategy says, no, let's be optimistic. Let's assume most people are good. So let's just allow them to tap the card on their own or not tap it on their own. Let's not worry about it. So everybody can get on the bus or the train very smoothly and very quickly. Now, in order to make sure that we do have the cards tapped, every now and then, while the vehicle or the train is moving, we stop it and we'll have somebody go over every rider and check their cards through through their phones or something. Check their card to make sure it's tapped. If it's not tapped, then they pay a big hefty penalty for not obeying the rules. All right, that's an exception-based strategy. So, and they call it exception because it happens not in a normal flow of operation. You do an exception. You do something different than the normal. Obviously, this approach will have a severe effect on everybody who's riding when the inspector comes, right? Because it may delay the trip, because it could create delays, but only on those random occasions when the exceptions is handled this way. On the other hand, in the defensive approach, you sort of amortize this process and have every person go through a small delay before they get on. Is a defensive strategy better or an exception-based one? Is really a matter, it's a case-by-case basis. If most people are trying to avoid paying, then obviously a defensive strategy would be better. On the other hand, if most people are good and only maybe 2 or 3% that try to avoid paying, then an exception-based strategy would be better. Let's see how while writing a Java program, we can have this choice of handling problems defensively or in an exception-based manner. So to do that, let me create a class let's call it exception class, or exception or defensive, something like that. And in this class, let's assume there is a method whose job is to do some computation. Let's do that defensively first. So this is a defensive calculation. I'm going to assume it takes 2 parameters, a string that I'm going to call S and an integer I'm going to call D. Let's describe briefly what this method is doing. This is an example or a demo of a defensive strategy, and particularly this method is going to display the integer in S divided by the integer D. So let's give an example also in the comment. So example, if the string S happened to be the string containing the integer 24, and if D happened to be 3, then this will lead to the method displaying 8, because 24 divided by 3 is 8. Simple method. So the algorithm that I will follow is what you would expect. I first have to extract the integer from inside the string. We've done that so many times. So let's call it integer n equal. I go to the integer class and pick the parseInt method to turn the string into an integer. And then I would have integer result being n divided by d. That's why I'm calling it n and d, like numerator and denominator. And finally, let me just display on the console result. So a straightforward implementation here. And just in a quick and dirty way to test it, I'm going to have a static method here that defines some string s, like 24, and some denominator d, like 3, and then I'm going to call this defensive calc method and send to it s and d. Notice that the method is void, so you just invoke it like this, and it will presumably display that. Let's test this just to make sure our algorithm is working fine. So I would say run this. As you know, the first time you do this, it's a bit slow because it's building the whole app, not just this class. But then hopefully things will be better. The run finished, and true enough, it says 8. So that's what we expect. Now, what could go wrong? We have to look at our program. Remember, we're doing things defensively, which means we have to anticipate each and every problem that may arise and guard against it. Make the program secure to plug that vulnerability, if you like. So many things I can think of. Let's go statement by statement. The first one said integer n equal this. If you go to the parseInt method in the Java API, it tells you its contract, and it says that if s does not satisfy certain properties, then an exception will be thrown by the method. And as you can imagine, if s does not contain an int, then asking the CPU to do this will be an invalid operation, and it will trigger an exception. So I'm going to just do a minor thing. I'm just going to add a space to the 24 and see if I run the program again what happened. And right away I see that an exception is thrown. And this exception, which happened to be in the Java Lang package, has a name. The class is called number format exception. So the method is saying, if you want me to extract the integer from inside the string, right, it has to have the int format. It has to look like an int. A space is not allowed, all right? So I need to do something to guard against this. So one thing that maybe comes to mind is perhaps I should remove all spaces or leading spaces from s. The string class does have a method called trim, and it removes not just the leading spaces but also the trailing spaces. So this way, before we send the value of s to the parseInt method, we are first trimming it, removing all spaces. Let me add a comment here so that we remember what happened. So to say, to avoid this runtime exception, which is called number format exception, we trim, all right? So we started taking defensive measures. Now if you run the program, you will see you will get 8 without having an exception. That's good. What else can go wrong? Well, What if the string s that we're sending happen to be null? All right. Remember, the string is an object in Java, so s is an object reference that refers to it. If the reference is null, that means there isn't even an object for the s reference to point at. So when you say here s.trim, the dot operator means I need to cross over from the reference to the object. And if there is no object, obviously I cannot cross over, and there will be a problem. If I run the code here, I get an exception. And the exception is called null pointer exception. That means you tried to invoke on a reference that is pointing nowhere to invoke some method. So again, I need to guard against this thing. So maybe I will add something here. I would say if the string you sent me happened to be null, and I'll put a comment and I'll say I'm doing this to avoid this new exception that popped, the null pointer exception. So if this happened, I will display something different. This is my handler, if you like. I'm going to tell the user s cannot be null. All right. Or maybe you should say the string cannot be null, since s is just a variable name that the user doesn't know. Otherwise, if this is not the case, then yes, you can go ahead and follow the algorithm as it used to do. So now if I run my code, which sends null, I get a clear message that says the string cannot be null. So the program did not crash. I did not have an exception because I added this, right? What else can go wrong? Well, many things can go wrong. S may not be null, may not have spaces, but it could be 2.4 instead of 24, right? Well, this also cannot be parsed into an int, and I suppose I need to put something in my code to say that there shouldn't be a decimal point in here, right? So yeah, there are methods in the string class that allow you to ask, is there a particular character or a substring inside a given string? And if that's the case, we need to issue an appropriate error message. Otherwise, we proceed. It could be worse than that. It could be this string is hello. That means it doesn't even have a number of any kind inside it. And again, perhaps we need to form a regular expression that filters out only integers inside the string in order to make this happen. So as you can see, many things can go wrong, and I need to guard against every one. All right. So that ultimately will take care of this parse int, if you really can think of every possibility and guard against it. How about the next statement that says integer result is n over d? Another thing can happen here, not related to the string, but related to d. If you send me d equals 0, so let's go back to a valid s like 24, but d is 0. Now if I run the program, thereby asking the processor to divide 24 by 0, I get yet another exception class called arithmetic exception. And the detail message does say divide by 0. So you say, no problem, I'll guard against it. Okay, so you would add an if statement that says if d is 0. So let's document that by saying I'm doing this to avoid having an arithmetic exception. If this happened, then maybe print a message that says the integer cannot be 0. The integer that you divide by Otherwise, we're good to go. All right. Now, if we run the program in its current state, no exceptions are thrown, but a nice error message, a clear error message, is printed. All right? And I'll leave it to you to think of other things that can go wrong and see if you can guard against them. Well, let's summarize the defensive strategy by saying, if you adopt it, you better anticipate each and everything that can go wrong, and you better be able to guard against it somehow, put an if statement, do something to detect it and prevent a crash from happening. And while we're describing the defensive strategy in general, let me add that there are generally two disadvantages that I see in such an approach, in the defensive approach. The first one is you're asking me to anticipate everything that can go wrong, and sometimes I may be able to anticipate 3 or 4 things, as I did, but there could be other things I couldn't think of. That's why if you want to try to make a program secure from a computer security point of view, you are in a cat and mouse race with the hackers, right? If you can anticipate every bad thing they can do, fine. Maybe you can build a program that is secure, but what if tomorrow they thought of something that didn't occur to me? So I would call that a disadvantage, a first disadvantage of this approach. The second one is readability. Look at this code now. When we started, our program was really nice. It's just a 2-liner, right? And it was self-documenting. The first statement in it was simply get me the integer inside the string, and the next one said divided by the other integer. We're done. Everybody can understand this. But then we added a trim, and there's an if statement here, another if statement here, and there are regular expressions to catch other possibilities. As you can see, these if statements are interleaved with the original program. This statement was immediately before this statement, but now they are 2 or 3 statements apart. And in this trivial toy program, if this method was really a real life kind of method, then it becomes much bigger, and reading it would be difficult. Anyway, so this is the defensive approach. Let's re-implement this method again. I'm going to copy the top part, but this time I will re-implement it in using an exception-based approach. It does the same thing, but it's not defensive, but exception. How do you do this? Well, you go back to the original program that we created before we secured it. So we had this. We didn't have any trim inside it. And we had those 2 statements. Our algorithm was really nice and simple. Sorry. All right. So now, rather than saying what can go wrong, let's take the optimistic approach and assume nothing is wrong and tell the CPU, please try to execute these 3 statements. You see, already it looks nice because our algorithm maintained its simplicity, its readability, right? Its self-documentation. So we're telling the CPU, hopefully most cases you have no problem, you're doing the calculation, we get the result, and we're done. However, in those exceptional situations where a problem occurs, and I know the CPU will throw an exception, we're telling it, let's catch the exception ourselves. So we say catch, and remember the exception in Java is an object, so I'm going to declare its object reference. Let's call it E, and this is the end of the method, right? And the idea goes like this. If things are fine without problem, then these statements will be executed and the method will exit. If anything went wrong, whether you anticipated it or not, control will transfer to the catch statement. Here, you can say system.out.println. You can tell the user that whatever parameter they sent you are invalid. So you can say invalid parameters. So now in the client code, if you call the exception method and send it something, let's start with something valid first. If I run it like this, I get 8. And if I add space here, I get a nice message that the parameter is invalid. If I put hello here or anything, it says invalid. If I divide by 0, it says invalid. And wow, this is the beauty of the exception-based approach. I did not have to anticipate what can go wrong, because I said whatever goes wrong, rather than crashing the program, get me the exception and let me print a message to the user. So I dare say now this method is crash proof. No matter what happens, right, it cannot crash because I'm catching that exception. And also the other advantage, of course, is that the algorithm implementation stayed simple, stayed together. It didn't get separated by if statements or trims or other things. All right? Now, I know some of you are thinking, yeah, that's nice, but the message you are giving the user is so generic. You just said invalid parameters. What if the user in an app filled a survey made up of 20 inputs, 20 edit texts? He made 20 entries, let's say, and then one of them led to an exception, maybe a telephone number that's wrong or a Visa number that's wrong, and then you say invalid. Well, the end user will not know exactly where the problem is, right? And why did it happen? Is it possible to make the resolution finer? Can we detect errors individually? And the answer is yes. You can catch several exceptions, starting with the most specific ones. So remember here we said if a division by 0, for example, the name of it was arithmetic exception. So you can first catch this particular one, the arithmetic exception, call it E. And now you know this happens when you divide by 0, then you can say system.out.println. Something like the denominator D cannot be 0, or whatever you want to tell the user, it doesn't matter. And if it was a different exception, like the number format that we found before, then we know that the string has a problem. So you can say catch that and display to the user. By the way, if this was a real app, the display will not happen in the main method. It will return a string to the activity, which will poke it in a toast or something in the view. So it will say here, the string does not contain an int, because that triggers this one. And finally, if other things happen, then I'm gonna catch the exception class itself, right? Those three classes, arithmetic, number format, and exceptions, form a family, a hierarchy, an inheritance hierarchy, with the grandparent being the exception class. If you go to the Java API and look at exception, it shows you all the children and grandchildren that it has. And since it is the parent of it, then any exception instance that happened can be pointed at by a reference of type exception. It's just like saying, if I have a variable of type double, can I give it a value which is an int or a long or a float or a char? And the answer is yes, because double has the most accommodating type, if you like, among the number family. Same thing in the exception object. The exception is the grandparent of all exceptions, right? It should be noted that the order by which you write the catch statement is important, because during the execution of the try block, if something wrong happened, the CPU is going to throw an exception of a particular type, and it will offer it to the first catch statement to see if it catches it. How do I know if it catches it or not? Well, it's just like saying, I have a variable e here defined to be of this type. I'm going to give it a value to force it to point to the exception that the CPU threw. If the exception is a child of this or equal to this, then it will work. Otherwise, the processing or the flow will go to the next one, and this one will be offered the chance to catch it. If it cannot catch it, you go to the third one, and so on. That's why it's really important that you put the big guy, the exception, last, right? Because if you put it first, then obviously it will catch any exception that comes about. This summarizes the exception approach. And again, as I said earlier, it has those two advantages I pointed out, and would be the preferred approach unless, as I said, you adopt a defensive strategy in a scenario where you know everything that can go wrong, and you have ways of guarding it. All right. So going back to here, now we know how the exception object work and how we can catch multiple exceptions. And that ends this part of the lecture.